All right. The next thing that we're going to talk about here in Unit 10 is going to be pressure. So, what we've got, oops, hold on, I'm going to show off my bubbles here. All right, Unit 10, we're going to go back to gases and what are called gas laws, and then we're going to start with this first section, which is going to be pressure. Okay, in order to define pressure, what we're going to do this is two ways. One, definition-wise, you've got pressure is the force per unit area on a surface. Mathematically, we can define that as pressure is equal to the force per area, or F over A. Now, we're not going to do a lot of math calculations, but it's important to know. So I always give the example of a shoe. If you had a sneaker and a high heel and you push them down with the same amount of force, the high heel is going to feel a lot worse because there's less surface area to disperse that against. Typically, the unit we use for SI is what's called a Newton. A Newton is 1 kilogram times a meter over second squared, so hence the reason they just use the term Newton on that one. And like I said, as the surface area decreases, pressure increases. We've all seen this, but the shoe is one of the best examples of those. Now, we're going to talk a little bit differently about pressure, not so much pushing on things from a solid perspective, but in related to gas. And the pressure exerted by a gas is going to depend on three things. It's going to depend on the volume of that gas. It's going to depend on the temperature, excuse me, as well as the number of molecules. Because the volume and the temperature are going to be indicative of how many times they slam into each other and how crowded they are, and the number of molecules is also going to play into part. And remember, for temperature and kinetic energy are directly related. So we're going to come back to the kinetic molecular theory a lot in this section as well. Okay, there's my equation. All right, so for measuring pressure, we use what's called a barometer, and you may have heard about this before, but it was an instrument first used to measure atmospheric pressure. It was first created by Torricelli in the 1600s, and it's a glass tube filled with mercury is inverted, or a fancy word for flipped upside down, in a dish. The mercury will flow out of the tube until the pressure of the mercury inside the tube is equal to the atmospheric pressure on the dish. Okay, what the heck does that mean? Well, here's the thing. If there's more pressure coming down from the atmosphere or somewhere, if there's more pressure outside, it's going to force the mercury in the tube to rise. So therefore, if there are little numbers on here, it's going to show an increased pressure. On the same token, if there is less pressure pushing down here, then it's not going to rise as much. So it may only have a reading of here. So that's where or just know that a barometer, we'll do these on occasion, but a barometer is going to measure pressure. Okay, now for units of pressure, we have to do some unit conversions because there are, about 4 or 5 different units. First one is millimeters of mercury. This came from the mercury barometer. Excuse me. Literally measuring how many millimeters that the mercury traveled. Okay, so you got millimeter increments, that's where it comes from. The torr, wow, is from Torricelli inventing the barometer. You have atmospheres, which is atmospheric pressure. You hear about this a lot with the weather. They talk about high pressure and low pressure. You also have a Pascal, or Pascal rather, just like Pascal's triangle, and that's 1 Newton over meter squared. It's an SI unit. It's named after the French scientist. And here's what's important. You have your conversion factors. These will be given to you. Okay, you do not have to memorize these. In fact, there's one other one that you need to add, which is 101.325 kilopascals. I'm just essentially doing that times 10 to the third conversion for you. But 1 atm is equal to 760 milliliters of mercury, is equal to 760 a torr. Yes, they're the same number. And then there are your values for Pascal and kilopascals. Because what's really important is we have to be able to do conversions for these. So let's set these up. If we have 0.927 atms, all right, we're going to put the 1 atm on the bottom, 760 millimeters of mercury on the top. Okay, and here's the thing, always use your data. There's 3 sig figs. We don't use conversion factors to limit sig figs. So our answer here should be 705 millimeters of mercury. Okay, now for torr, it's going to be the exact same math problem, except that the unit is different. It is what it is. We can't get rid of them, so we do still have to know that they're 760 torr. in 1 ATM, so we get the same answer. Your calculator actually gives you 704.52, so it's going to be 705 torr. And then for kilopascals, we start with 0.927 ATMs. We go to 101.325 kilopascals, right? 1 ATM. Again, we're going to use our data, 3 sig figs. To get, your calculator gives you 93.928. It's going to be 93.9 kilopascals. Okay? Pretty simple, pretty straightforward. Let's do a few more. This time we're going to have 148.6 kilopascals. We're going to go 2 ATM. So remember, whatever we're going to goes on the top. Whatever we're coming from goes on the bottom. Essentially, your unknown is your from. Okay, your unknown is your to, and what you're converting, your known is your from. So here you're going to have 101.325 kilopascals. Since it's on the bottom, we're going to divide. So it's going to be 4 significant figs in our data. It should be 1.467 ATMs. Okay, now millimeters of mercury. We're again going to start with 148.6 kilopascals. All right. We're going 2 millimeters of mercury, so 760 millimeters of mercury. And again, from the 101.325 kilopascals. So we get to take 148.6, divide it by 7, multiply it by 760, get an answer, take that answer, divide it by 101.325, and we end up with 1,114.59. So we're going to round that to 1,115 millimeters of mercury. Now to save time, torr is exactly the same setup. The only difference is that you're going to have 760 torr on the top, so you're still going to end up with, little time delay there, 1,115 millimeters of mercury. Remember, you're going to be given those conversion factors. You don't have to memorize them. Okay, the other thing we got to talk about here is Dalton's Law of partial pressure. Same John Dalton that was responsible for atomic theory. He also studied gas mixtures. And this one seems pretty obvious to me, but it was not recognized at the time. But he states that the pressure of a gas mixture is the sum of the individual pressures of each gas alone. So in other words, what that means is that however many pressures I have, pressure of each gas exerts in the mixture is independent of the other pressures that are there. So they're each their own entity, but when you're looking at the total pressure, you just make sure that you add it up. Okay, so the other way, it's the total pressure of a mixture of gases is equal to the sum of the partial pressures of each component gases, no matter how many there are. So in other words, your pressure total is just equal to pressure 1 plus pressure 2 plus pressure 3, etc., etc., etc. And I know this seems really obvious, but I'm going to show you where we can do some of the math here. Partial pressure is just the pressure of each gas in the mixture. Why? Because the particles of each gas in the mixture have an equal chance to hit the proverbial walls of the container. And those hits are what form the pressure in the first place. Okay, no different than if you're pushing on something. The pressure exerted by gas molecules this time is the actual collisions that they generate. So each gas exerts pressure independently, Total pressure is the result of the total number of collisions per unit of wall area. Okay, so how many collisions are there per the space allowed to divvied up? Okay, so here you've got a smaller number of particles, there's going to be more, and then you're going to just have more because there's more gas molecules floating around. Okay, water displacement. This is a type of lab where the gas produced is less dense than the water, so it replaces the water in the bottle. So here we're heating the solid substance, and as we're heating it, one of the products that we're getting is oxygen gas and water vapor. And so actually one of the products we get is oxygen gas. So the oxygen gas is going to travel through the tube, and they're going to pass it through some water vapor. Okay, because here is the water. So then pass it through water. So then over here you have oxygen and you have water vapor. So if we know the pressure of one, we can figure out the pressure of the other because of, so the pressure total here would be equal to the pressure of the oxygen plus the pressure of the water. So the gas collected is not pure because it contains water vapor. So like I said, the pressure total is just equal to the pressure of the gas, so this one, the oxygen, plus the water. And we can use that to solve mass problems. And the equal to the atmospheric pressure. So if we're running a lab, we just measure the atmospheric pressure in the room, and then all we have to do is know the water, and this is temperature dependent. So you would be given the pressure of water vapor at certain temperatures, and then you could solve for it. There you go, set for a certain temperature. Okay, I was smarter than I thought I was. All right, so for example, oxygen gas from the decomposition of our potassium chlorate was collected by water displacement, exactly like you just saw. Barometric pressure and the temperature during the experiment were 731. So our known is 731.0 torr for the total pressure, and the temperature was 20.0 degrees Celsius. The partial pressure of water vapor is 17.5 torr at 20 degrees Celsius. Okay, that's what's important. So our, I'm sorry, this should say pressure total, not capital T. So now if our pressure of the water is equal to 17.5 torr, this math is super simple. We want to know the pressure of the oxygen. So all we have to do is have Dalton's Law, which is pressure total is equal to the pressure of the oxygen plus the pressure of the water. We know the total pressure. You don't have to plug the 20 in anywhere. It's just the only reason you need the 20 degrees Celsius is to tell you the pressure of the water. So 731.0, we're looking for the oxygen plus 17.5. It's a simple subtraction problem because we got to subtract 17.5 from both sides. One decimal place here, so we should end up with 713.5 torr for the final answer. And that's it. Wow, 713.5. If I just said that correctly. All right, last thing you got to know is this is something you just got to memorize. What's called standard temperature and pressure at STP is exactly 1 atm in 0 degrees Celsius or 273 Kelvin. You just need to know this, and we will do more problems in class. Okay, I hope that helps.